In this presentation, we're going to be talking about this year's senior design project for the Biofrontiers department at UCCS. Just a little bit about Biofrontiers. They're an institute of the University of Colorado that performs multidisciplinary research in physics, mathematics, engineering, computational sciences, and biology. Specifically, the primary sponsor for this project is Dr. Guy Hagen, who conducts research using fluorescent microscopy techniques to image and study single cells, as well as studying other forms of microscopy techniques. So to help with Dr. Hagen's research, this year's project was to design and build a fully functioning dual objective microscope. A dual objective microscope is a microscope that features two opposing objective lenses. So basically, this combines an inverted and a non-inverted microscope in a single structure. This allows the two microscopes to focus on the same point on a sample and take an image of the sample from both above and below. This is useful because it greatly increases the resolution you're able to observe a sample with. Especially in conjunction with fluorescent microscopy, you're able to capture the fluorescence emitted from the sample from two directions, which allows the microscope to effectively image single cells, whereas single objective microscopes can usually only image multiple cell samples. In addition, using a dual objective microscope can produce a 3D image of a sample by superimposing the two captured images over each other. This can be seen here, where the green pictures on the left are the images captured by each lens, and on the right is the reconstructed 3D image of the sample. So overall, the goal for this project was to come up with an effective design for an upright dual objective microscope, and then build that design using the microscopy components provided by the sponsor. And then the structural components would either be fabricated by the team or purchased through third-party optical outlets.
The engineering specifications report had 10 requirements for the dual objective microscope. These requirements were broken into structural and image requirements. The first of the structural was the device must be stable, which meant that it had to be able to withstand bumps and small disturbances. The second was the device must be compatible with the Olympus MLN objectives line. The third was the device must incorporate the XY platform and the Z-plane adjustment plate. These were purchased previous to the project, and the sponsor wanted to be able to incorporate these into the dual objective microscope's design. The device must be compatible with both large and small cameras and allow for replacement and removal of microscopic components. The device must allow for the addition of the filter box, which is used in fluorescent microscopy techniques. The device must allow for removal of one side of the microscope's components and used as a single objective microscope. This means that either the inverted or the non-inverted side could be removed from the microscope, and the other side that remains can still be used as a single objective microscope. The camera, tube lens, and objective on the device must be precisely aligned to a singular XY position. The image requirements included the device must incorporate a source of illumination, which again falls back into the fluorescent microscopy technique. The device must utilize coarse and fine adjustments, which are used to focus on the sample, and the device must produce a clear image. The image was verified by the sponsor to be within an acceptable clarity.
Conceptual design. Having ironed out all of the engineering specifications, we learned the required positions of each of the essential microscope components and their narrow range of tolerances for their movement. Having this information, we needed to design a support system to hold them. Our main concern was keeping the components in the non-inverted and the inverted side aligned, and our solution was to support all of them to a single support beam using 5 separate arms. The first diagram shows our solution for the stationary stage mount, which would hold both stages and the sample being viewed. Next, we have our objective lens holding arm, which would attach to a fine movement apparatus, and the whole arm would allow coarse movement along the support beam. Finally, we designed one more stationary arm, which would hold the camera, filter box, and the tube lens. Both of these last two would be identical to be used in both the inverting and non-inverting side. We later moved the stages to a separate support system and combined the latter two arms into one for each side, which simplified the system immensely. In addition to the support system, we also needed to design an adapter plate to attach the Z movement stage to the XY movement stage. Seen here on the bottom, it screws into the upper Z stage and is held in place by the bottom ring shown, which fits nicely into the hole going through the XY stage. On the side here is the SolidWorks assembly model that would show what the conceptual design would have looked like had we not refined it further.
Alrighty, so the testing of our microscope wasn't as a more concrete testing. We didn't really have concrete answers other than we just checked by criteria, which the criteria was a pass-fail, and the pass-fail criteria was whether if the microscope abided by the engineering specifications, and the main one being if everything was aligned and if everything was stable and still, and if we believe that if all the components could be supported by each other. And so the strategy was test as we go, and the reason why I say it was test as we go is because initially we still had to order parts that we had incorporated into our design. And so our testing began with first designing the tube lens adapter, in which we initially made the first one, which is the picture on the top left. And so what we realized with this adapter was that it was too wobbly, and so we didn't want to risk the stability, because when you're looking at a mechanism under the microscope, it has to be super, super still in order to create a nice clarity picture. And so because of that, the second tube lens adapter, which is shown in the picture right below, was created, and this increased our stability by a lot, and it firmly held the system together. And so with this first phase of testing, which was a prototyping phase, the adapter plate was also made, and we realized that within the first go of testing the adapter plate, this also passed our pass-fail criteria. And so the next phase in that would just be recreating it into the final material. And then along with the prototypes that we had tested, we had some design changes, in which the design change was really just the rail that was the support rail. Initially, we had decided to use a 35mm rail, but we later found out that this rail wasn't going to provide enough stability for everything that we're attaching to it. So we had changed this rail to a 95mm dovetail rail. And along with the rail, we initially, as a team, wanted to design arms that everything would be going on to, but we had realized that with the tolerances, they were we didn't have much room to make a mistake. And so in order to keep this controlled, we decided as a team to just go ahead and purchase the arms that would attach to the dovetail rail in order to create something that's very precise and identical in both for the top and the bottom part of the microscope. And so for the second phase of the testing, this was really just fully assembling our microscope. This happened after we had all our parts together, and so with the second phase of testing, we had realized that everything worked pretty well together. And so the only issue that we had in the second phase of testing after we had fully assembled our microscope was that we had realized that we didn't leave enough room for when we used our large microscopes. And so, or not the large microscope, sorry, when we use our large cameras. And the reason with that is that we didn't consider the cords that attach to the ends of the cameras. So we had later then adapted the design to add slag mounts or stage leg spacers, along with an extension to the support rail.
All right, so the final design of the project was mostly designed around eliminating unnecessary components, making the entire thing easy to alter into different microscope practices, as well as leaving enough room for everything that needed to fit in this, as the final design came to about 3 meters tall. And most of what was put into the final design were purchased components due to their complexity that we couldn't redesign or fabricate ourselves, and due to the extremely tight tolerances that were required to keep everything lined up so that we could actually get an image through all the components. So the parts that we ended up fabricating ourselves came down to the 4 listed on the screen. The first component fabricated was the sample platform adapter plate. This was made to attach the platforms to each other so they can move in unison. This one provided the most difficulty in fabricating, as we didn't have proper engineering specifications for the stages that we were going to be attaching to each other. So we had to do a lot of measurement and essentially guesswork in making this. The final product did come out very nicely, though. It made everything very stable and gave us what we wanted. The next component we developed was a 3D printed tube lens adapter. This gave a nice tight hold to the tube lens and made it secure nice and tightly so that there wasn't any camera shaking. This also allowed us to attach the tube lens directly to the filter box, which in turn allowed us to eliminate one arm from each side of the device. The next thing we developed were the stage legs and stage legs extensions. These allowed us to get rid of another support arm that would have been required to hold the sample stages to the main support structure. And then with the extensions, this gave us the versatility to change it from an inverted, a non-inverted, or a dual purpose microscope, and gave us the necessary height requirements that we needed for the larger cameras. The final component that we made was the support structure legs. These were required as our support structure wasn't tall enough to hold on to attach everything to it, and once again it gave us the height we needed for our cameras.
In conclusion, we were able to construct a fully functioning dual objective microscope, which is pictured here in the BioFrontiers lab, as well as produce a SOLIDWORKS design package of all the components designed by the team, as well as a schematic of the full microscope, so any components can be reproduced and reassembled anytime. This final design was decided to meet all the engineering specifications for the project, and we hope it will be very useful to Dr. Hagan and the other researchers in the BioFrontiers lab in their future research. Thank you very much.
Kyle Albright.
Olivia Rader.
Logan Rudig.
I'm Markel Shoy.
Corey Trenchik. The design team was asked to develop a method of analyzing skeletal motion. This design idea is primarily focused on aiding in bone fracture analysis when an individual experiences a fall. The design should incorporate a 3D model of the subject and allow for accurate motion modeling and data output. Initial constraints presented to the team included available funding as well as functionality of the design system for a variety of skill levels and technical understanding.
Based on market research and client intent, some following design requirements were established, which would be captures all desired data, cost-effective, portable, and usability. From these design requirements, some engineering specifications were established as well. Along with cost-effective, the client had a requirement that there was a $3,000 cost limit. That included all equipment and software and hardware. For captured all desired data, any data collection must have been taken between 10 hertz and 50 kilohertz. This was just due based off other research from other competitors and how their motion capture systems were established. Along with this, force-slip measurements accurate to within 10 newtons were also established. This had to do mainly with pressure analysis, and again, just based off of other competitors and how they were able to conduct their research. For collecting data and visualizing it, at least 2 coordinate axes were required for the portion of the body to model in any dimensional space. As far as modeling and animating the body, 3 coordinate axes were required for this, and that would be sufficient enough to animate the body in any software. For imaging and any cameras used, at least a resolution greater than 0.3 megapixels was chosen due to weight and cost considerations. And as far as portability, the equipment must be small enough to fit in a backpack or briefcase. This is just due because the motion capture system will not be in a lab or in a set space, so it must be able to be carried around and portable, which is also due to that. It should be, 15 pounds or less than 45 pounds, whether it's being wheeled or carried by hand.
The team explored several different options as possibilities to meet the client's needs. Included in these options were cameras, bodysuits, body markers, and force plates. For using cameras, the idea was to create a system of cameras surrounding the subject. Images obtained from the different camera angles would then be combined through programming to create a 3D model of the subject that could be displayed on a digital device and analyzed accordingly. Bodysuits are something people are likely familiar with as they're used in movie making to create CG characters. The bodysuit is a suit that covers most of the body and has sensors sewn into it to obtain motion data on different points in the body in order to produce a 3D image. Body markers, also known as inertial measurement units, can be attached to different points on the body, especially locations near joints like the elbows or knees, and are then programmed to communicate with each other to determine accelerations and orientations at those points and to create a 3D image of the individual wearing the markers. Force plates are plates that someone can stand on and that will measure the forces being exerted on the plate from different points on the individual's feet. Force plates could not stand alone as a motion analysis system, but could be used as a supplement to another system. The team used a design selection matrix to weigh the various design options against each other and determine which design or combination of designs would work best. Because bodysuits have to be made for the build of the individual who wears it, the team determined this would create limitations on testing. Force plates would require extra bulk as well as a lot of setup. So the team decided that the cons outweighed the benefits of the force plate. The main considerations in determining between camera system and body markers was portability and cost. Cameras would require more setup time, would take up more space, and would be more equipment to carry. Body markers, on the other hand, would be much lighter and easier to transport and not take up as much space. In addition, body markers were found to be much cheaper than good quality cameras. As a result of these considerations, the team decided to use body markers.
The final design is composed of a suite of inertial measurement units, or IMUs. IMUs are equipped with accelerometers, gyroscopes, and magnometers. These components give the IMUs the ability to record data such as acceleration and orientation. The IMUs are designed to be placed in 16 spots strategically around the body. This would provide a digital representation of the subject. IMUs are secured with adhesive and bands in positions that don't restrict movement or interfere with data collection. The IMUs communicate and are coded with Arduino. Arduino has open source libraries for IMU data collection such as this. It will collect the desired data needed to compute data such as forces and torques on the skeletal structure. The final design was to be lightweight and easy to use for all demographics.
The team chose to go with the SparkFun 9 Degree of Freedom IMU based on reviews and results. The team used open source codes found on the Arduino website. The team encountered an issue with getting the codes to work with the IMUs. The original Arduino failed to work properly due to an issue with the system. Several troubleshooting methods using a multimeter were used to determine if this problem was a result of hardware or software. The issue arose in getting IMUs to communicate properly with the Arduino. The code would not spit out any information. During the design phase of the project, the team encountered an issue with the COVID-19 pandemic. The team was working with a resource from the University of Colorado, Colorado Springs, to troubleshoot the code. This resource was no longer available after UCCS shut down. The team was no longer able to obtain more hardware for the design after the shutdown due to extended lead times and shipping from sources. Without more IMUs and the ability to test the Arduino, the main scope of the project was altered. Prior to the stay-at-home orders being implemented, members of the team were able to meet and rule out some possible issues with the equipment.
While the team was unable to produce a working prototype based on circumstances outside of their control, a design solution was determined that could accomplish motion analysis. The final design package for the motion analysis system includes a detailed diagram of the placement locations of the IMU sensors when worn on a person. A bill of material structured as a hierarchy to illustrate the final assembly and subassemblies of the system is also included, which shows how the prototype should be built. A user manual with the Arduino setup, a program download option, the troubleshooting methods, as well as the means to download the software to read the Arduino code is also provided. All of the Arduino codes to determine the collected necessary data for the motion analysis is found in the appendix, along with a test code to show whether or not the Arduino is communicating with the sensor. This concludes the Spring 2020 Senior Design for Motion Analysis.
This presentation is for skeletal imaging improvements. The sponsor for the project is Dr. Todd Bredbenner, a professor at the University of Colorado at Colorado Springs. The UCCS senior design team consists of Sabrina Ball, Jonathan Bremer, David Johnson, Lindsay Nast, and Samuel Knopfsiger. Osteoporosis is a common cause of vertebral fracture, where current research in the prevention of fragility fractures is limited. Calculations to predict an individual's risk of fracture and current fracture risk models are inaccurate. This is due to the lack of parameters and the difficulty in safely retrieving this information. Trabecular bone structure is one of the many factors that play into determining this risk, but this is hard to determine from typical medical low-resolution computed tomography, or more commonly referred to as CT scans. Low-resolution imaging data of bones is more readily obtainable compared to that of high-resolution data. However, by using micro-CT scans, trabecular bone structures can be determined, but at the risk of exposing patients to higher doses of radiation, as well as increased expenses. Therefore, the need for a method to obtain micro-CT data from low-resolution CT scans is the intent of the senior design project. Examples of different resolution clinical CT scans can be seen in figures 1, 2, and 3, where figure 1 displays a low-resolution scan of a lumbar bone with the lack of detail regarding bone attributes. Figure 2 displays an image with more defined, fine details at a higher resolution. And figure 3 is a segmented image of figure 2, where only high-density regions of the bone remain in the image, and the porous layer of the bone is visible.
We use quality functional deployment methods to understand and gather our customers' requirements and then choose the best possible method. In order to completely understand our customers' requirements, we started off with meeting with our sponsor, Todd Bredbenner, and gathering his requirements. The first requirement that several potential methods must be researched and evaluated was chosen because information regarding the output fabric tensor is needed in order to go from low-resolution input data and end up with high-resolution data. In order to fully understand and select the appropriate method, It is crucial that research was done to accurately select the best method. We met and talked with Emily Henning, a graduate student working for our sponsor, who would use our project to assist in the overall research. She emphasized the need for an automated method that was user-friendly. This means having the option for a visual input, such as a CT scan input, that would be the easiest and most desirable outcome. Next, we set up a meeting with Ryan Rieger, who also works with Dr. Bradbrenner as another voice of reason. In speaking with Ryan, he provided a lot of detail into what was needed for a satisfactory method. To begin with, the proposed method will have a quick calculation time because Dr. Bradbrenner referred to 800,000 sets of images that would need to be processed, and that even a 1-minute processing time would result in 1.5 to 2 weeks of processing time. Next, the proposed method will accept a low-resolution CT input because of all of Dr. Bradbrenner's data is low-resolution CT input. For the requirement of the chosen method will produce a high-resolution directionality output, whether it be an image or set of data. This means data can be gleaned from the trabecular structure and is easier to interpret visually, such as a picture or 3D model rather than a raw set of data with numbers. For the requirement, the proposed method will have a cross-functionality platform. This allows for our process to function under any platform, ensuring the ease of use and ability to share acquired data with all colleagues. The final requirement of the proposed method will have functions for multiple types of bone is because of errors produced from the limitations of the database based on one bone type. In order to not have these errors, being able to analyze more than one type of bone will improve accuracy and efficiency of the prediction of the trabecular bone structure. The first parameter, the minimum accuracy of the output must have an error of less than 10%, was chosen to define how well the project requirements for output and flexibility with regard to bone, though it was also found to correlate strongly with user-friendliness and cross-platform functionality. The second parameter, the resolution of the input CT data and output of any form, was chosen to relate to both the clinical resolution data available to the project and the length scale needed to observe the fine structure of trabecular bone. The third parameter was chosen as a processing time of less than 30 seconds for any input. Input data must be processed quickly to work through the large amount of data in a single CT scan, much less the number of CT scans needed for any potential studies conducted by the sponsor. The fourth parameter was taken directly from the requirement that the project takes clinical CT data as input. Standardizing this input, particularly with regard to input data type, file size, encoding, and other software-specific attributes, dictates how well the system can be automated and lessens the potential for human error. The final parameter was derived from a need for a user to interpret the highly directional nature of the required output, which, when examining potential methods for this project, was done by creating a field of local anisotropy vectors or done innately through super resolution.
When we first started our research, we had 7 possible methods to help solve our specific problem. We used a decision matrix and scored each method based on their compatibility and the parameters described in the design requirements. The 4 best scoring methods were the database analysis, super resolution GAN learning database, orthotropic high resolution finite element models, super resolution using convolutional neural networks. Once we slightly reduced the number of methods, it was easier for us to research more into the 4 methods chosen. After we felt like we had a better understanding of those 4 methods through more in-depth research, we narrowed our methods down again, so we only needed to focus on 2 methods. Those 2 methods that we chose were the database analysis and the super resolution GAN learning database. The GAN learning database covered a comparison of the performance of the GAN circle to other state-of-the-art methods, where it was determined that the GAN circle retained better anatomical information with sharper visual results when compared to the database model. However, limitations exist for this method, including a long training period. The database analysis uses a database of high-resolution bone images to be able to compare the low-resolution image to a higher resolution image, and therefore we would be able to approximate the trabecular orientation. With a small database derived from a sample size of 33 high-resolution images, and matching the low-resolution image to a higher resolution image using only one parameter, there was already a significant increase in the accuracy compared to only isotropic models.
So the final design package is a set of MATLAB functions which take a set of segmented micro CT images, such as the one on the upper left, as an input, and then outputs the distribution of bone volume density in that image, as well as the fabric tensor for that image. The way this works is it takes the input image, one image at a time, then breaks it into blocks of pixels comparable in resolution to clinical CT images. Then each of those blocks is averaged to calculate the bone volume density, where the white dense features of the bone have a value of 1, and the black, less dense soft tissues and such have a value of 0. So this returns some decimal number between 0 and 1, which is then saved. The distribution of these over the image is saved as a separate image, such as the one on the lower right. So this distribution of density is the clinical CT comparison data. This is what we will be comparing the clinical data to. So we then need to calculate the mean intercept length of the image at each. So we then need to calculate the mean intercept length of the image for each angle theta between 0 and 360 degrees. The way this is done is the program draws lines at 1 pixel intervals at some intercept angle theta across the entire image and records both how long the total length of lines drawn is and how many times those lines intercept the white features of the image. So the mean intercept length for some angle theta is the total length of the lines drawn at that angle divided by the number of times it intercepts the image features. So that data was then plotted on a polar plot, such as the rows plots on the bottom left, sorry. It was then fit using a least squares method to an ellipse. That's the red line in that image. The quadratic form of that ellipse, where the ellipse has some form ax squared plus 2bxy plus cy squared equals 1. The quadratic form of that ellipse is a matrix where you have A, B, B, C. The eigenvalues of that matrix and their associated eigenvectors are the fabric tensor of the image. That's the directionality information for the image's microstructure. So that tensor can then be calculated and associated with the bone density distribution from the previous slide. And then those two pieces of data can then be exported to another file to serve as a long-term database or can be used immediately in another MATLAB program.
At this stage in product development, the database has been constructed is based on 2D images or single slice micro CT scans. In the future, it would be advisable to translate the code to accept 3D images or multiple layered slices of bone. This would allow the comparison of volumetric bone mineral density, VMBD, and therefore have closer comparisons and more accurate results. After this is done, there will need to be a code that will take the VMBD of input low-resolution CT scans and compare them to that of the database and choose the image from the database that has the least error. Once the image is chosen, the program will take the fabric tensor and orientation of the database image and apply it to the input scans. There are a few ways in which the current program can be improved. The program should have a user interface that will make using the code easier. Currently, users must edit the source code to choose the input files, format the output data, change the resolution of the bone volume fraction grid, get diagnostic data, and develop graphical representations of any data retrieved. All of this can easily lead to breaking the code and or obtaining data that is unclear or wrong. The current program is also computationally expensive. The mean intercept length component specifically requires a calculation and logic check at every pixel in an image. There have been alternative methods to calculate or approximate the mean intercept length of an image, and some of them may be worth investigating, particularly as the program moves into calculating voxels from multiple CT slices. There will also need to be testing and validation for the comparison code. In the original source paper, one image from the database was taken out, downgraded, then used as an input to check against the remaining database and evaluated to determine the percent error as compared to its original values. A similar process of running a new input with known values should be run through the program as well to ensure accuracy and precision of unrelated images. The parameters used for comparing the input to the database can be increased as well. Thus far, the only parameter that is required is the bone volume fraction, a ratio of the volume of mineralized bone per unit volume of the sample. The program could possibly be improved upon by including parameters such as bone type and or shape, patient traits such as age and gender, medical history, particularly of diseases like osteoporosis, rickets, leukemia, or any other that affect bone fracture risk. And lastly, increasing the size of the database would allow for increased overall accuracy. While databases as small as 30 samples can be quite accurate, as a patient pool increases, some of the inputs may have increased error when compared to the relatively small database. It should be noted that increasing the database is rather trivial with this program, and the main limiting factor would be the acquisition of new micro CT scans. We'd like to take this moment to thank all of you for listening to our presentation. We'd also like to thank Dr. Bredbenner for providing his support and input, as well as Emily Henning and Ryan Rieger for their contributions in helping the team determine useful requirements of the design. Thank you very much.
My name is Fahad. Our project is going to be about novel food delivery. For our design, it can be used in many markets, but we're focused primarily on hospitals. The current tray got some problems if it's used in hospitals. It has spilling problems, everything is too loose, and heat could escape easily. Especially since there could be a lot of patients, there would be a lot of spilling accidents, and food would get cold easily until it gets delivered to every single patient. And since our tray can be in closed configuration, it can prevent way more heat loss than the regular trays. And we're focusing not only to prevent it from heat loss, but we are also making sure that it's very easy to use and easy to deliver from the kitchen to patients, making sure it can be used daily. It can hold variety of food and drinks, whether it's cold or hot, of course. Making sure the tray is lightweight, easy to stack, and prevent spilling in any way in closed configuration. So in our design, we did a lot of research and designed it in a way to make sure that if a delivery person drops a tray by accident, the tray would be very difficult to break, and he doesn't have to worry about food getting spilled all over the place. He doesn't have to worry about cleaning up the mess he made, going back to the kitchen and making the meals again. No, none of that. All he has to do is pick up the tray and put it where it was in the cart. Very easy and a time saver. And the tray would have everything the patient needs, different compartments for food, drinks, silverware, napkins, and even salt and pepper if he needs it. Now Jonathan is going to be talking more about design specifications.
Hey, I'm Jonathan Richards. I just want to quickly discuss some of the design specifications and requirements for our product. So some of the more important specifications and requirements include that the tray must be able to fully close to decrease contamination through transit between kitchen and patient. The food must be kept between a specified temperature range throughout the process. The tray in open configuration must have raised sides and rears to decrease chances of spilling up to a given angle, and it must be stackable in both open and closed configurations. So we did have a few notable requirements that were eliminated after testing, and some of those included incorporating heating elements to maintain a greater temperature in the tray, Handles located around several points of the tray, including top, sides, rear, and also we wanted the separate components, sides, lid, and the back, all to be able to be folded underneath the tray in the open configuration while the patient is eating or pulling out the tray. So these designs were eliminated just due to the fact that either they hindered the structural integrity of the tray or they introduced risk to the patients through burning of the heating elements. And that's just a few of the handful of requirements addressed with the, designing the tray.
Okay. My name is Jasmine. Yeah. So I helped take part in the testing. Initially, I did the hand calculations, the finite analysis of the hand calculations, and they needed, the walls of our tray needs to be a specific thickness for injection molding and dropping or smashing of the tray based off of a hard surface like concrete, the kind of material they have on hospital floors. After doing the hand calculations, we got that it should be between 0.02 and 0.1837 inches thick. Somewhere between there will be fine to fall. So in the end, after 3D modeling it and getting the numbers a little more condensed, in SolidWorks, we ended up picking that most of the things would be 1/8 or 3/16 of an inch.
I am Felix. Originally, when we designed models, the tray in SolidWorks, Colin already conducted a lot of research to determine the best thickness for injection molding. So each part was already assigned a specific thickness. After we did the testing, it turned out that the thickness, most optimum thickness required to withstand the stress and abuse during daily use of the tray was pretty close to the thickness that Colin assigned to each part when he was modeling the tray. So we decided that we will keep the original thickness this way. The tray will be a little bit stronger because the thickness originally was a little larger than what the test showed. So the tray will be slightly stronger. In the meantime, the weight increase is very minimal. And in addition, the tray, all the parts will be optimized for injection molding, which helps to decrease production costs. So that concludes the testing. Now, move on to user instruction. I'll summarize it very briefly. So first, when you assemble the tray, you just slide down all the panels and the lid and put in the cups and the sub-containers for the bread and crackers. Very simple and easy to use. Very intuitive, anyone can figure out without even reading the instructions. For meal preparation, all you have to do is to slide off the lid and remove the bread and cracker containers, which will be filled with bread and crackers. Then you can put in all sorts of food into the food compartment. You can fill your cups with beverages and put in the cup slots. Then you put in the silverware and the salt and pepper shaker. Then you can put the bread and cracker containers back in and slide on the lid. Then you're ready for delivery. During delivery, because all the food and utensils are enclosed in a sort of sealed space, which significantly decreases the possibility of contamination and reduces heat loss. During use, the user simply removes the lid and put it upside down to the bottom of the tray. This does two things. First, it does not take up any extra space, unlike a conventional lid, where you have to find a place to put it somewhere. Two, there is a gap now between the bottom of the main tray and the lid, which functions as the bottom. So when you put it on your lap, it doesn't burn you, no matter how hot the food is.
Hi, my name's Colin Bennett. I did a lot of the final design work in SolidWorks for our novel food delivery tray. And I'm going to be talking about some of the features that we included and kind of the final design process that we went through. For our tray, as Jonathan has mentioned in a lot of our engineering specifications, we had several very important requirements that Steve wanted us to meet. Those requirements included the tall sides of the tray in order to avoid spilling things if the tray was tilted, the ability to separate different main food compartments in order to hold multiple types of items. There are cracker trays and sandwich trays or bread trays that fit inside of the main food trays that all needed to be nested inside of the main design, as well as cups that could be taken apart, their handles from the cup that needed to fit into the tray and fit below the lid. All of these things we worked over the course of a couple of months, trying to figure out different dimensions and size constraints that would fit within the overall design of, I think it was 11 inches by 18 inches. We came up with this final design with the sliding walls and back in order to make the tray conform to one of the requirements, which was that the design be injection moldable. In order to do that, we couldn't have certain undercuts. The thickness of certain parts needed to be within certain tolerances, and the tray overall needed to be made out of a plastic that they're able to use in injection molding in order to make the tray more flat for travel and things of that nature. The cups and the food or the bread and cracker trays as well are separate features that are molded outside of the tray, but they nest within the tray. The cup cutouts and the bread and cracker trays fit neatly above the soup container and the main entree container, excuse me. Another feature that we like to incorporate was the ability to hold multiple sandwiches in the bread and cracker trays. If it ended up that you wanted to hold up to, I think, 8 sandwiches was a requirement that Steve wanted us to fulfill, and we were able to do that. Finally, the overall design of the tray met his desire for the lid to be able to be removed. It can slide underneath in order for easy storage, and the tray was able to withstand all of the FEA testing that we did, and withstood the drop test, the test for rigidity, the test for stackability, and all of the other tests that mean the product will stand up and be usable for many years to come.
Hello, this is Dylan Welsh. I worked for Cobham over the summer of 2019. I worked in finite element analysis and modeling of Cobham products to make predictable, decent lifespan predictions of Cobham products. The big important part of that phase was the epoxy underfill material that they use in their products. They use it to combat things like solder fatigue and die cracking. So to make accurate predictions, we need to have really good material data, and the manufacturers don't release adequate data that's suitable for FEA analysis. On the Cobham UCCS team, we have Jeff Lurch, Chris Carter, Sean Glover, myself, Joseph Sandoval, and Madison Zainowski, who is the main lead. Next slide. So a bit of Cobham's background. Cobham produces integrated circuits for aerospace applications. Epoxy underfill is often applied to flip chip packages assemblies to combat solder fatigue failures caused by cyclical thermal loading. The underfill epoxies must withstand extreme temperature changes, which they are likely to encounter in field environments. Epoxy has a different coefficient of thermal expansion than that of die and substrate in the integrated circuits. This raises concerns for product reliability during thermal cycling in the field. Cobham needs accurate material property data required for finite element analysis, FEA, which aids in predicting the expected lifetime of Cobham products in various field environments.
Hi, I'm Madison Zankovsky. And our requirements, we were tasked with determining a specimen manufacture procedure as well as a testing procedure to obtain the young modulus required for their underfill epoxies. We were looking at doing 6 samples for 3 epoxy materials, tested at 2 different strain rates, and then due to the COVID situation, we ended up changing the requirements to actually obtaining the Young's modulus to just providing a testing procedure and specimen manufacture procedure, as well as requirements or recommendations for the next team to continue this process.
My name's Chris. I'll be talking about the flat specimen cure and production process. We began with a cylindrical idea, but that was scrapped, and we went with a flat specimen based on the recommendations of the materials testing department of UCCS. The mold is manufactured of aluminum 6160 and is prepped with 3M 180 grit fine sandpaper, and then coated with a liberal application of DuPont Teflon nonstick dry film lubricant. The liquid epoxy has to be stored at a negative 40 degrees C, so it prevents long-term curing at room temperature. It is thawed at room temperature and then injected into the mold before it is placed in the oven. About 30 cc's of epoxy was used for each of the samples that were tested. The samples are cured in an oven for 2 hours at 165 degrees Celsius, and then removed and allowed to cool at room temperature before the mold is disassembled and the square or rectangular sample is removed. Next slide, please. After the sample is removed from the mold, it was then passed off to the members of the UCCS machine shop to be shaped in a CNC controlled mill. And after receiving them back from them, a Dremel tool with a sanding head was used to level out any uneven surfaces around the edges as final preparation for the testing process. This diagram shows the exact measurements that were used by the CNC mill to cut the fillets into the previously rectangular samples for tensile testing in the Instron machines.
I'm Sean Glover, here to talk about the testing equipment and procedure. We use the Instron 5569, which is the smaller of the 2 Instrons on campus, and we use that partially because it already had the right load cell in it, and because it was connected to the computer, which made it a little easier to set up the programs. We used the 50 kilonewton load cell, which is the smaller one available on campus, because the lower load cell size allows for better resolution of the data, since epoxy samples don't have that much strength to tension. And of course, we use the Blue Hill Universal software that runs the Instron, and we use the extensometer, which can be seen on the lower left. The way that works is it clips on with those 2 wire clips on the far left, which push the sample into some blades on the ends of the arms, which is designed to give very accurate strain data, very accurate lengthening data, which we can turn into the strain, because the strain gauge on the Instron itself isn't as accurate. There's a lot of mechanical linkages that get taken up in the process and can throw off your data. This provides an external reference, which is more accurate. Slide, please. So the procedure was placing the sample in the clamps shown. It has to be calibrated before it's placed in. You balance it, and then you take measurements of both the part being tested with the calipers available in the testing lab, and you also gauge the separation of the fixtures on the machine itself, measured from the edge of the actual clamp touching the part to the edge of the other clamp. Then this is torqued in using the torque wrench to 40 foot-pounds on each bolt, 10 foot-pound increments, with the top grip first and then the bottom grip, because it is possible and unavoidable for the grips to shift somewhat while tightening. And it was found out that if you tighten the top first, then you're less likely to apply torque stresses to the part before you test it. Then once the part is in the machine and everything has been measured, the test is performed at a fairly quick rate of 5 millimeters a minute or 1 millimeter a minute. And the system automatically captures the data from the instruments for later analysis.
Hey, this is Jeff. So before we get into our data, we want to talk about two topics: raw data and salvage data. So essentially, salvage data is the export of raw data that comes directly from the Instron machine and the Blue Hill software, and then the raw salvage data is what we parse by inspection to just the linear region. So if you look at the top left plot there, you can see a nominal engineering stress strain plot with expected results. It has minor slipping, clear elastic region, and a brittle fracture. Moving to the right top figure, you can see that the actual salvage data plot looks very similar to that raw data. We were able to use almost all of the data from that raw data test. Looking to the bottom left, you can see that this is an unexpected result, and major slipping is present. There's compression, as well as the elastic region being unclear. Because of that, we had to parse that data into just a salvage data form, or the chart or the plot on the bottom right that shows the salvageable linear region. For orientation, there is the R squared value as well as the trend line in the top right of each plot. Next chart. Next slide, please. So we were able to do 7 tests, and the elastic modulus results, basically we're able to paint in the corners of the box. We were able to obtain results from 340 newtons per millimeter squared to 5,080 newtons per millimeter squared. Two of the 7 tests showed nominal testing results, and those were between the window of 3,000 and 5,000 newtons per millimeter squared. It didn't matter what the strain rate was. All linear trend line regions had an R-square value that exceeded 0.99. And basically, our engineering judgment tells us the true elastic modulus is going to be somewhere in a span of 3,000 to 5,000 newtons per millimeter squared. The gold star plots at the bottom there are the nominal tests. The purple star plot in the bottom right is a test that started off as expected and then began to slip. And the table towards the right shows all of the obtained values, where in green we have what we expect to be the true range of elastic modulus, and in red the outlier values. Next chart.
I'm Joseph Sandoval, and I'll be wrapping everything up. So the requirement of our UCCS design team was to find modulus elasticity for epoxies at room temperature. To do this, we used a existing mold and CNC machining to produce testable samples that we can later break in the Instron. 6 samples were produced overall that we could get usable data from. Results varied from 340 to 5,080 newtons per millimeter squared. We can conclude using engineering judgment that the modulus elasticity we're looking for is between 3,000 and 5,100 newtons per millimeter. So we weren't able to find an exact value for the modulus elasticity, partly due to COVID, but we do have a methodology that we can pass on to next year and they can find value.
Hello, this is an expo presentation for the Collins Aerospace Senior Design Team. The members of our team were Bradley Chesney, our team leader, Dylan Stravette, our CAD designer, myself, Norman Anderson, the spokesperson, and Madi Almazidi, the machinist, and then Luke Bergstaller, our technical writer.
So the main purpose for this project was to design a recline mechanism for Collins Aerospace so they can input it into their aircraft pilot seats. The main reason that the company wanted to do this was so that the pilots could have more eye positions so that they could see their components better. So in order to do that, they came to UCCS and asked the senior design team to design recline mechanism with more degrees of freedom. So, and this of course would allow for a pilot to be able to recline farther back and at more positions so that he or she can see his controls better.
From the problem scope, we came up with a set of problem specifications with our sponsor and with the rest of our team. The first one is that the recline mechanism shall withstand a static, proof, and ultimate load of 2,665 pounds force and 4,000 pounds force, respectively. The second one was that the recline mechanism shall not exceed a total weight of 2 pounds. The third one was that the recline mechanism shall not be able to withstand 10,000 full cycles, with a full cycle defined as unlock, full recline, and then decline and lock. The recline mechanism should also not be allowed to exceed $1,000 worth of expenses with a nominal amount of $500. The fifth specification was that the recline mechanism shall allow for full upright position of 10 degrees with a tolerance of 1 degree and from vertical, with the range of recline to 35 degrees from vertical with that 1 degree tolerance. The sixth specification was that the recline mechanism shall provide infinite or at least 1.5 degrees increments of adjustment. This was the most important specification we focused on, as that's kind of where their initial problem scope came from. And then the last one was that vibrations will be considered in the design of the recline mechanism.
All right, so when we got to the final design, like Brad stated, the 1.5 degree increments of freedom was the most important. So our final design is the top left figure here with the triple pin connection arrow up here. We've got our pin housing, the side clip, and we've also got our plate here that has the 3 rows of holes that we designed for. The best thing about this design is it does meet that requirement exactly at 1.5 degree increments of adjustment. We ended up taking the same pin sizes, same plate design, same materials to retrofit to their current seats, which was definitely a preference from the sponsor at Collins. As you can see up here, we've got the plate down here on the arm of the chair where the pin sits inside their seat. And so our plate here and our mechanism will attach to the arm of the seat here. We were also talking about the triple pin connection, which we designed for, which would allow all the loading pins to unlock at the same time. And to actually make this work, we would have to implement a cable system, which is this idea here. So there would be a cable that attaches from the handle on the current seat to the triple pin connection here, which is also shown up here as well.
All right, so for the next couple of slides, I'm going to be talking about the static analysis for both the plate and the pin housing of the recline mechanism. For the plate, it is made out of 4130 steel. And if you look close enough on the image in the center of the slide here, you can see that there's 2 types of arrows. there's a green arrow and there's a purple arrow. Now the green arrow basically represents where the plate is fixed and or locked, and the purple arrow represents where the force applied is. And you can also see that there's different colors on the plate, and each color basically represents a different stress. And that's represented on the right hand side here on the von Mises stress chart. Now you can basically see that the highest stress recorded on the plate is about 1.7. Yeah, it's basically the highest stress is basically a lot less than the yield strength, and so that basically gives us a factor of safety of 4.15, which is very, very good. So for the second slide here, we can see basically the same thing, but for the pin housing. On the right-hand side, you can see the stress is recorded on the pin housing, and the highest stress recorded on the pin housing is also less than the yield strength. And this basically gives us a factor of safety of 1.52, which is also above our goal. Thank you.
All right, so when we're talking about static analysis on this mechanism, we definitely needed to do some free body diagrams, figure out how we're going to apply loading. When we were first designing for the mechanism, we had 4 bolts that were going to hold this, but we soon realized that we had to upgrade to 6 bolts. First, I'm going to show you this diagram over here. What we have, this is going to be where the pin housing sits. The seat arm is going to be on the top of the diagram. So we knew that the highest stress that's going to be created inside this mechanism is when the furthest outside pin is being loaded, which is going to be down here. We also knew that distance where the pin is going to hit the pin housing there. And we also could calculate the bending moment based on our force calculations on the pin. Once we knew the moment here, we could use the line of loading from the force over to where the bolts are going to be sitting. And we also were concerned more about the tensile loading on the bolts than the compression side. So from the diagram, we actually have 3 bolts in line here going into the page. And then there will also be another set of 3 on this side here. Since there was only 3 bolts in tension, we did divide that full bending moment or loading here by 3 to figure out what the loading would be on each bolt. Once we did that, we were able to design for the bolt size, the thread size, and once we had that information, then we could determine what the ultimate tensile factor of safety was. That turned out to actually be 1.4, which is actually a good factor of safety. The only thing is it is an ultimate factor of safety, so you could expect some yielding going on inside the bolt. However, the size of the mechanism did restrict us on how large of a bolt and nut combination we could do. So we actually ended up choosing the best option that we could for our design. 1.4 was the factor of safety there. We also wanted to look at the shear factor of safety along the seat arm. And this was also a big concern because typically the shear strength is a lot lower on any kind of part, like a bar or a bolt, compared to like a tensile loading or compression loading. So it was definitely important to analyze. We actually got a yield factor of safety of 1.33, which means that it's actually not even going to yield at all in shear loading. We also were able to divide that shear loading by 6 because there is 6 bolts holding the shear loading itself. Next, we got to the frustum analysis. It's basically a stress analysis inside of the materials. It's going to be basically talking about stiffnesses of the materials in the pin housing and also in the seat arm. We did come to the conclusion that originally we were going to just bolt just a single bolt into the side of the arm, but it is made out of aluminum. So it wouldn't be the bolt that fails first under the calculated loading. It would actually be the threading inside the arm of the chair. So we actually came up with this idea to do a counterbore the size of the nut. And also, since the nut is going to be a high alloy steel, just like the bolt is, we were able to actually make that ultimate tensile factor of safety 1.4 compared to it failing with the aluminum threading as well. The left side here is just our frustum analysis diagram, some of the equations we used. Another important point too is we were able to calculate the preloading and pre-torque for the bolts, and it would actually work out better with this counterbore anyway. So all in all, this little change actually worked out quite well.
For the vibration analysis, we decided to take into account all the parts that were either modified or created. So we wanted to see if any of the natural frequencies of these parts would match the input frequency for the plane. The highest frequency for the plane that was given to us by Collins was 2000 hertz. So from this table, as you can see, none of the natural frequencies of these parts meet 2000 hertz. So this means that the design for the recline mechanism will not approach failure.
Load testing on the mechanism would be conducted with a static proof and ultimate load of 2,600 pounds force and 4,000 pounds force respectively. The duration of the load would just last until that load is reached, and then it would be reduced. And the pin that's engaged inside of the mechanism would be the one farthest from the chair, because that's where the most stress on the mechanism and as a whole would be seen. And you could see where the pin farthest from the seat is indicated by the red arrow. And then the seat rest would be where the blue arrow is pointing.
Here's the justification table based on the initial work specifications that we were given by Collins and came up with ourselves, compared to what we met in the actual final design. So for the first one of the mechanism being able to withstand the static proof and ultimate loads of 2,600 and 4,000 pounds force, we did a static analysis both on hand and in SolidWorks to determine that it would actually pass that test in theory. And then also we got a mechanism weight of 1.7 pounds, which is 0.3 less than our goal. For the 10,000 full life cycles, we use the same plate and pin materials, as well as a suggested powder coating to reduce the wear on that. Besides that, we had a estimated cost of $250, which is considerably less than the $1,000 that we were originally going for. The mechanism was also designed for the requirement of being able to go from 10 to 35 degrees from vertical position. As described before, the most important one was that we met the 1.5 degree increments of adjustment, and we did exactly that. And the vibrations were considered in the analysis and done in Fusion to prove that each part's natural frequency did not resonate at the same natural frequency of the plane, so that it wouldn't approach failure.
Overall, the senior design experience was a good one. The team worked very well together. Our communication was top notch, and our sponsor was very good at communicating with us and making sure that we had everything that we needed in regards to just files and specifications and specific numbers and material and all that stuff. So we were able to achieve what our sponsor wanted, but we weren't able to actually make the prototype, which was the only downside to this whole experience because of the COVID-19 that's happening across the world right now, and us not being able to be in groups and being able to be on campus. We weren't able to make a prototype to send to Collins and actually see if our design would work on the actual chair in regards to the analysis and the computational stuff, everything is solid. It's just getting that final just check mark of saying, yes, we made this out of the materials and it's just plug and play and it actually works. That's the only downside to this whole experience. Other than that, we all had a great time, and we just really enjoyed this whole experience.
Hello and welcome to our senior design project, feedback control demonstrator. Our team includes Emma, Shelby, Cody, Caesar, and myself, James. Our project's sponsor is Dr. Lenan George. This project's objective was to build a feedback control demonstrator which will aid high school students in understanding higher level theory and hopefully become more interested in STEM fields in their future. Many high schoolers may still be deciding what they want to do after they graduate, so exposure to these ideas may help them decide that a STEM-based career is right for them. This project is sponsored by Dr. George, who has been a professor at multiple colleges in Colorado Springs. She has a strong Air Force background with years of lab research, teaching, and project management at bases across Southwest United States. Since 2007, she has been a board member of Cool Science, a nonprofit program for kids here in Eastern Colorado. Cool Science is a program intended to get kids interested in STEM by providing live demonstrations and lessons in classrooms and at local community events. We were given $500 to design, test, and build our demonstrator. This leads me into what controls actually is. Feedback controls is a way to adjust part of the system's output or response only by changing what happens in the system and adding a controller so that we can leave the input alone. Lots of theory and math go into how these behaviors do what they do, but we are mainly just aiming to adjust error, oscillation, and overshoot with our demonstrator.
While incorporating the 4 types of controllers, the differences of oscillation, steady-state error, and overshoot need to be explained and easily seen. The design needs to be able to fit through classroom doors since that will be the primary location of use. One person, the instructor, must be able to carry it his or herself. 30 pounds or less will satisfy this specification. To ensure simplicity with this design, the setup must not require any tools or software. The goal is to make it as easy as possible to use, especially if the classroom the robots are being used in does not have access to a ton of technology. Just like any product design, safety is a high priority, even more now that the design will be used in a setting with children. A user manual needs to be provided that includes important definitions, safety, reference documents, anatomy of the design, setup and operating procedures, preventative maintenance, and a troubleshooting guide. To assist the instructor actually doing the demonstration, lesson plans that include outcomes, equipment, and activities in a supplemental PowerPoint with notes will also be provided. A live demonstration also needs to be completed. The 6 designs that were brought up while brainstorming include a balancing ball, inverse pendulum, line bot, jousting robots, gumball drop arm, and a threaded arm with claw. While looking how well we believed each design would satisfy the requirements compared to our datum, the line bot, immediately the balancing ball, threaded arm with claw, and inverse pendulum were eliminated. Once we narrowed it down to 3 designs, we did a numerical comparison with the 3 designs that tied. The Nerf gun got eliminated due to safety concerns. At this point in our decision of which design to use, we were left with the jousting robots versus a line bot. The jousting robots were chosen as the design, and the justification was because we figured it would be more interactive, fun to look at. The drawing shown here was the conceptual design of the robots. The computer module could either be an Arduino or Raspberry Pi. The chassis design with 2 motors and a caster wheel is what we believe to give the best range of motion. The body of the robot would act as a platform for all the other components. The jousting arm will be attached to the body and primarily used for the PID demonstration and can be removed for all other controllers. The power storage is an obvious necessity to power the robots and also can be recharged as needed. Possible sensors that could be used include a line tracker, accelerometer, gyroscope, and/or a camera.
The following parameters, along with a brief description of what they will accomplish, were tested to ensure sponsor requirements are met. Power consumption testing will determine required battery capacity and quantity per demonstrator. Temperature testing will ensure operating temperatures are maintained below dangerous levels to maximize safety. Accuracy testing will ensure sensors' capabilities to provide suitable data for best performance is achievable. Weight testing will directly address the weight requirement from the sponsor. Power consumption testing provided data that was critical in determining individual and assembled sensor and system load, as well as battery capacity requirements. Temperature testing was essential in determining the potential safety hazards that each robot may expose an instructor or student to during a live demonstration lesson. Accuracy testing focused on the system's ability to provide the data necessary to demonstrate the 4 different controllers, P, PD, PI, PID, as per the sponsor's requirements. Weight testing directly addressed the weight limitation requirement of the entire project set by the sponsor. It was concluded that the final design would successfully satisfy the requirements put forth by the sponsor while only requiring the addition of a second battery. But the motor battery being the bottleneck of the system, a demonstration can ideally last approximately 2 hours and 10 minutes. These sensors were deemed sufficiently accurate to be used to demonstrate the 4 different controllers with additional adjustments within the Python program. The temperature outputs of the motor controller and computer module were deemed safe for operation by staff or students in any educational environment. The entirety of the project weighs less than 30 pounds and can be transported in a vehicle and by hand without any issue.
The design involved bringing many components together that create a product that fulfills the requirements outlined by Dr. George. Also included in the critical design, the operation of the robot was outlined along with documents including the user manual and lesson plan. The design was built using components that were both acquired and produced by the team. With the complexity of the design, the team chose to use some components that were available to purchase. These components of the design are readily available, are low cost, and are highly reliable. The Raspberry Pi sensor chassis, including the motors and the batteries, were all bought from online retailers. All acquired components were modeled using software. From the model assembly, the components that were produced by the team could be built using the same software. The components that were made by the team include the spacers, body, jousting arm, and the mat. The design uses 3 different spacers. The first 2 are used to raise the Raspberry Pi and the motor controller off the chassis, while the 3rd spacer is used for the line tracker sensors as they need an offset from the ground surface. A large part of the modeling that the team completed was done with the body of the robot. The body is used to encompass all of the electronic components, keeping them from being damaged or keeping the user from touching any sharp or hot parts. The body is also used as a mount for the ultrasonic sensor, camera, buttons, the motor controller switch. The final use of the body is to hold the batteries. Both the Raspberry Pi and the motor controller batteries are held on the top of the body. The robots are powered on by plugging in the Raspberry Pi battery and turning on the motor controller using the switch located on the controller buttons. The robot is then placed on the mat and allowed to load for approximately 1 minute. Once ready, the robot is then placed on the track. Pressing any of the 4 buttons will commence the robot to move forward while following the line. The program will run for 30 seconds, and then the robot will come to a stop. From this point, any of the buttons can be pressed, allowing the same or different controller to be shown. To further the demonstration, both robots can be running at the track at the same time to help visualize the difference between the types of controllers. The final demonstration places both robots opposite of each other on the line track. Using PID, the robots will joust. Here's a video of one of the robots on the track using the PID controller.
After the design, testing, and building of the robots, each of the requirements from Dr. George was met to the best of the team's ability. For the controller specification, all 4 controller types, P, PI, PD, and PID, were demonstrated by the robots. The budget set by the Colorado-Wyoming Alliance for Minority Participation was maintained. Dr. George contributed to the final 3D printing of the body due to the closure of the UCCS machine shop for the last half of the semester. The robots, container, and instruction manual altogether weighed less than 30 pounds as specified. The total weight of the project was 15.46 pounds. The dimensions of the carrying case are 37 by 21.25 by 17.75 inches, so it can fit through a doorway. The case also has wheels for ease of transport. For the setup specification, there is no need for an electrical outlet when using the robots, and no extensive setup is necessary. The temperature testing completed by the team showed that the robots will remain at a safe temperature during use. Ultrasonic sensors were also employed for student safety. They will guarantee that the robots will not hit a student. The team wrote a lesson plan and created a PowerPoint to accompany the demonstration, and a practice demonstration was filmed by the team. However, an actual demonstration could not be completed with a group of students due to COVID-19. Possible improvements to the robots or to the demonstrator would be the use of analog line trackers rather than digital. While digital line trackers provide live feedback, analog control theory was the focus of the controllers being taught to students.
Hello and welcome to the MEE Senior Design presentation for the Orbital Mechanics Demonstrator. So to start, we are going to have everyone introduce themselves. So I'm Amanda Termes.
Hi, I'm Caleb Sen.
I'm Ryan Sandoval.
I'm Matt Ellis.
Christopher Williams.
All right. So to start, our sponsor for this project is Dr. George. She is a professor with UCCS. She teaches a bunch of different courses, including the astrodynamics course, which this project is intended for. The project basics. The problem that we are trying to solve is in regards to the demonstrating of the different ways that orbits are talked about and how they are explained. Initially, students are given a little whiz wheel. However, this device is very small and it's really hard to teach in a classroom setting to all of the different students. So she asked us to create a larger model that can be used in front of a classroom so that it's easier for all the different students to see from different angles, and so the COEs can be understood by every student.
So I'm going to talk about the project specifications. I'm going to go over how we determined each of the specifications, what process we used for that, and then I'll go over all of our 19 specifications that we came up with and go over some of the most important ones, which are the classical orbital elements. So initially, we developed some of these specifications through Dr. George. We met with her weekly and kind of picked her brain and decided what would be best for this project. Additionally, we met with some other students who have taken astrodynamics. We interviewed those students, kind of asked them what they thought was important in a orbital device in which they can learn in class. So they told us what they thought they were important. They brought up their own ideas, and that way we didn't overlook anything. And so that was another way that we decided on some of our project specifications. Next, the United States Air Force Academy, or USAFA, has an orbital device that they've used for many years. Unfortunately, this device does have some long-standing issues. The device would fall apart often. It was extremely costly, and it was very heavy. And so it had some issues that needed to be fixed. And Dr. George used to be a professor at the United States Air Force Academy. And so she saw how this item could be beneficial, but it wasn't due to the issues. And so actually Chris and Matt both went to USAFA in person and took a look at the device, took some notes on it, and used this information to help us with our specifications. So we analyzed all this information that we got from everybody and came up with 19 solid project specifications. The first one is all of the classical orbital elements must be displayed clearly. The eccentricity and semi-major axis must be predefined with known ranges. The right ascension of ascending node, or RAN, must rotate through 360 degrees. The inclination must rotate through 180 degrees. Longitude must rotate through 360 degrees. Argument of periapsis must rotate through 360 degrees. The minimum spacing for degree readouts for any of the COEs in which I just mentioned is 5 degrees. The product must use the geocentric equatorial reference frame. To replicate the real world view of how the orbits would interact with Earth, the product must be able to tilt on its axis by 23.5 degrees. So that way it really replicates the real tilt of Earth. The final product with the cart included must be able to fit through a standard US doorway. That way Dr. George can take it with her to class. And that doorway size is 36 inches by 80 inches. The product must separate from the cart and not exceed 20 pounds of weight. That way it's easily movable. The fully assembled product will be turned on its side and then weighed on 2 scales in order to find its center line as well as its center of gravity. It will not fall over when it's set off its axis by 10 degrees. It will be able to go through the standard US doorway, but be large enough to view in a large classroom setting. That way everyone can see it and it's still teachable to a large classroom, which is one of the main goals. Dr. George can assemble and move around all the elements on it under 2 minutes. That way it's quick and it doesn't take away from classroom time. The cost will not exceed $500. The product will be safe, no sharp edges, won't fall over and hurt Dr. George. And finally, if we can do it, the alternate COEs would be an added benefit, but not a requirement. And those are our project specifications.
For the concept generation, each member of the team was tasked with coming up with a unique design that would satisfy all of the different specifications that Ryan just discussed. The first of the designs was from Caleb, and it consisted of metal discs that were mounted concentrically on a cart. All of the designs generally had the same concentrically mounted ring concept, and the main differences were how they were mounted, how the inclination was to be adjusted. One of the designs had four pillars that would be able to raise and lower. One of the designs had fixed inclinations, and one of the designs had a mount or a base that could tilt and be supported. And the final design had basically was like a lamp shades, like a lamp on a cart that was able to tilt. All these designs were put into a decision matrix and they were compared against each other. And the final design took the best elements that we considered from each of the separate designs to be able to satisfy the concept and specifications most effectively. The proof of concept was designed, or was generally taken to from the concept design, was slightly modified. The initial design had a different way of, my dog, mounting the rings together through problem solving, moving forward from the conceptual design. The proof of concept used mounting plates to hold each ring and was used as a way to show that the design was actually able to function on a small scale.
So
this proof of concept also revealed some issues that we found. Firstly, having to deal with the way that the rings were mounted. We used hardware that would unfortunately make contact with some of the clamps and the braces, and then to secure the rings concentrically so that way they wouldn't interfere or slide laterally in their guides. We used stop gaps, little rectangular stop gaps that would fill the void in between the discs. Those proved to be a large issue because they would contact the hardware, the discs. They would make rotating the discs in the guides very choppy and not smooth. On top of that, if you want to move to the next slide, you can see these issues here on the proof of concept really clearly. The stopgaps shown on the left would contact pretty harshly, causing the rotation to be not smooth and choppy. We also found that the stopgaps would actually interfere with the hardware shown in the second picture. So we had to work around that, make sure that the spacing was even on the final design, so that way this would not be an issue. And then another issue that we found was that the clamps could rotate freely because they're only secured with one bolt, screw, nut assembly. This would obviously be an issue with retaining the discs, as if we flipped the entire inclination over and the clamps are not aligned, this could cause them to fall out and what have you. So this moves us into the final design. Chris, if you want to talk about that.
All right, so the final design addressed all of the issues that Caleb just brought up in the proof of concept. We changed the stop gaps to be not rectangular. So any of the cutouts where the hardware fit in did not catch on anything as the discs were rotated. Here in the picture at the top, you see a little piece of wood that allows the reference frame to be tilted to 23.5 degrees. We also had all of the discs laser printed and etched. These were done with SolidWorks, sending over some files that are available and ready to be printed again if anything breaks. The brackets that hold the disc together were changed a little bit so that the disc could slide a little bit easier, so that the rotation is nice. Yeah, is there another slide that has more pictures?
No, this was the only one showing the final design. Other features include the clamps that could hold two sets of hardware to ensure that the clamps are able to stay in place always, and it is repeatable, meaning that you can always make sure that they end up in the same place. The globe in the center features a protractor attached to it, so that way the inclination can be shown, and the center disc, so that way we had infinite adjustment on the true anomaly. Features a sheet metal, a piece of sheet metal sandwiched between the discs, so that way a magnet can stick to the top of it. This allows it to move quickly, freely, and easily, and can be set on either shown orbit on the bottom right-hand picture without issue. We also have large arrows showing the IJK vectors, the normal direction, the right ascension of the sending node, and anything else that was deemed necessary. So, in conclusion, the final device was capable of displaying virtually all orientations of an orbit. While we only used 2 different eccentricities and semi-major axes for the shown orbits, these orbits can be moved and positioned in almost any way around the globe, so we can show a variety of different values and factors. With the machining and laser cutting of the acrylic, it's highly visible and the indicators are clear and concise, so that way they can be identified by anyone and can be seen by anyone. The sizing of the final device was well well thought through. It means that it's portable and well dimensioned, so that way anybody can use it and it can be moved between buildings and classrooms without issue. And finally, the device, without considering the outsourcing due to the COVID-19 pandemic, is inexpensive and easy to maintain and repair. Each of the pieces was relatively inexpensive, and the whole thing together was less than $400.
Thank you everyone for watching our presentation and for paying attention and caring about our project. Thank you and have a wonderful day.